So I mentioned this in the last video on complex conjugates. We're now going to look at actually solving equations, roots of quadratics, and how they do occur in complex conjugate pairs when we have real coefficients. So if we have a quadratic equation, we'll use z this time since we're dealing with complex roots. If z is if A, B, and C are real numbers, so if we have real coefficients, so if they're members of the real numbers, then and there are complex roots to this, they occur as a complex conjugate pair. So if one of the roots is z, the other will be z star. That's how it works. We can also write, we tend to write when we get roots of quadratics, and we'll come on to this when we do the roots of polynomial chapter, we tend to write roots as alpha and beta for a quadratic, alpha being the first root, beta being the second root. If it's a cubic and you've got 3 roots, you have gamma as the third root. That's just how we write it. And we can always write our quadratic as z minus alpha and z minus beta equals 0. So alpha and beta are the roots, just like having if x is 3 and x is 4 for a particular quadratic. We know they must have come from brackets that look like this. So we can write it like this. Exactly the same with the complex numbers. And if we expand this, we'll get z squared minus beta z minus alpha z plus alpha beta. And then we can take out z and we can take out the negatives, so you get minus alpha plus beta z, plus alpha beta. And this comes into our polynomials chapter as well. This is minus, this is the sum of the roots, alpha plus beta, and this is the product of the roots, alpha beta. We're going to come into a lot more detail on that as well. But we can write the equation. If we've got particular roots, we can always find the equation. We can always write it like this: z minus one root, z minus the other root, and then we can find our quadratic equation from that. Let's get stuck into these examples here. So this is number 1 on this section. So we're given that alpha is 7 plus 2i. So that's one root of a quadratic equation with real coefficients. State the value of the other root, beta. So very simply, if the quadratic's got real coefficients, then beta, the second root, will be the complex conjugate, because they always occur in complex conjugate pairs if there's real coefficients of your quadratic. So there's the other root, beta. Find the quadratic. So in order to find the quadratic, we've now got both roots, so we can write z minus root 1 and z minus root 2 equals 0. And if we work this out, if we expand all this, then we can simplify it all and we'll get our quadratic. There are other ways of doing this. I prefer a slightly different way of doing this with alpha plus beta and using that, but we'll come on to that. We've not done that yet. And it's good to know both ways. So here we're going to get z times z, which is z squared. We're going to get minus 7 minus 2iz and minus 7 plus 2iz. And then you can get minus times a minus. So it'll be plus, and you're going to get 7 plus 2i, 7 minus 2i equals 0. It's by expanding these brackets. And we can expand and simplify this. So we get minus 7z plus 2zi minus 7z minus 2zi, so they will cancel. And I'm going to get plus 49, 7 times 7, minus 14i plus 14i, 2i times minus 2i, minus 4i squared, so plus 4. These will also cancel. So we're going to get z squared minus 7z is minus 14z. 49 plus 4 is 53. So we get the quadratic there that would have given us these roots. And if you want to, you can just stick it in your calculator and you can check. If you put your calculator in complex mode, put this in and solve it, you should get these two roots. So you can always check you've done this right as well, which is quite nice. Always nice to know that you're right. Find the values of alpha plus beta and alpha beta and interpret the results. Okay, so we will come on to this in more detail in future chapters. But alpha plus beta is just 7 plus 2i plus 7 minus 2i, which is 14. The imaginary bits cancel. And alpha beta, we've actually already done in that previous bit. But we're going to get 49 minus 14i plus 14i. minus 4i squared, which is plus 4. The imaginary bits cancel, so you get 53. So you should notice it says interpret these results. This relates to this, but it's negative, and this relates to this. So the sum of the roots is minus the sum of the roots. This is the coefficient of z, that's what we can take from that. And the product of the roots, 53, this is the constant term. Okay, and that will always be linked. So the sum of the roots of the quadratic minus the sum of the roots of the quadratic will always be the coefficient of the z term, or the x term if you're dealing with x's. And the product of the roots, alpha beta, will always be the constant term at the end. Okay, we will do loads of this, so don't worry. That's question 1. Question 2. The question 2 is z is 5 over 3 minus I. Okay, so again, as soon as I see that, I want to times top and bottom by 3 plus I based on our last video. And in fact, part A says find z in form A plus bi, where A and B are real constants. So the first thing we're going to do is take this times top and bottom by the conjugate of the denominator. 5 3s are 15, 5 times I, 5i. We're going to get 9, we're going to get plus 3i, minus 3i, and then minus I squared is plus 1. So simplify the bottom. Again, we know we're going to get this to cancel. We get over 10. 5 is common, so we're going to get 3 over 2 and a half if we just split it at the same time. So A is 3 over 2 and B is a half. So all that's in the previous video, all that stuff. On the second bit, so given that z is a complex root, so this is z here, that is a complex root of this quadratic, x squared plus px plus q equals 0, where p and q are real integers. So they're real and they're integers, that's important as well, so they're members of the integers. Find the value of p and the value of q. Okay, so if we've got one of the roots of our quadratic and the coefficients are real, then the other root must be the complex conjugate. So we can reverse that. So we've got both our roots, and then it proceeds exactly as we did in the last question. So we can then write z minus the first root, z minus second. Again, I've got to be very careful with signs and brackets. The root is made of 2 things, isn't it? 3 over the real part and the imaginary part. 3 over 2 and a half I, or 3 over 2 and minus a half I. So we've got to make sure it goes in a bracket. We include it in a bracket. Equals 0, and if we expand all this and simplify like we did the last question, we should get our quadratic. So z squared, we're going to get minus 3 over 2 minus a half I times z, and then minus 3 over 2 plus a half I z. Minus times a minus gives us a plus, and we get 3 over 2 plus this, 3 over 2 minus this. Okay, just treating this like this, z times this whole bracket, and then the same with the second term in the first bracket. This one times this, and this one times this. Equals 0, and then simplify. So we get minus 3 over 2z plus a half zi, minus 3 over 2z minus a half zi, so we can get rid of them straight away. 3 over 2 times 3 over 2, top by top, bottom by bottom. 3 over 2 times minus a half I, top by top, minus 3 over 4, bottom by bottom I, and then plus 3 over 4i, and you'll start to spot this. These little things cancelling each other out. Half I times minus a half I is minus a quarter I squared, so it'll be plus a quarter. Tidy up, so we're going to get z squared. We've got 2 of these. There are z terms, so we're going to get minus 6 over 2, or minus 3z, 9 over 4 plus a quarter is 10 over 4. We can simplify 10 over 4 is 5 over 2. Do that in stages if you want. So there's our quadratic. Remember, we were told though p and q have to be integers, so these have to be whole numbers. So we're going to have to multiply it by 2. To get it in the required state. Well, it'll be x, won't it? And we should be done. In fact, I think there's a bit of a mistake with the question here, because if we're writing it like this or like this, then it's in this form, but p and q are integers. But if we want to get p and q as integers, we do have to times by 2 like I've done to get it in this form. Well, I say times by 2, that should be a 6 as well. When I put by 2 in this form, I now don't have the correct coefficient of x. So the question must be phrased wrongly here. Either they want p and q to be, they could say real numbers, in which case you'd want this as your answer, or they could say like r x squared plus px plus q, where r, p and q are all integers, and then I would have to put it in this form because then they're all integers. So the question here is poorly worded. It should be more or kind of less specific, I suppose, depending on how you look at it. But this is definitely, these are both correct answers for this. One where we've got integer coefficients and one where we don't. Always read that they do like to have integer coefficients, so they do like to times up by that 2 at the end. But both will give the same roots. That's it.